Manuel Vázquez from the University of Madrid. Manuel started out his PhD actually in Madrid. He did his postdoc in the Technical University of Denmark, then returning back to Madrid, where he's been now for 27 years. And through that time, many accomplishments that he's been running through in terms of starting up IEEE sections within Spain, the chapter. He acted as the Intermag chair for Spain in 2008, president Magnetic Society in 2017-2018, and he also got the Distinguished Service Award in 2022. So over that long storied history, many accomplishments and many publications and many contributions in terms of volunteer work for IEEE. So today I would like to welcome Manuel Vázquez to speak with us. I'll hand it over to you, Manuel.
Okay. Okay. Can you see the first slide?
Coming through perfectly.
Okay. Thank you, Chris, for the introduction. So actually, I'm very sorry I cannot join you in Minneapolis. Because I wanted to be there, but because of the different appointments with other people, it's going to be impossible. So at least I can give you my talk virtually. So as you see, the title of my talk is Cylindrical Magnetic Micro and Nanowires. I will be talking about different points related to these different families of magnetic wires. Well, the first, it is our duty as distinguished lecturer to present this first slide, introducing some of the activities of the IEEE Magnetic Society. Although I guess it is very well known for you. You have your own chapter in the Twin Cities. So I just wanted to emphasize the activities related to education, to the summer school, which is very important for for the PhD students, that they can attend the summer school where all expenses are covered by the Magnetic Society. And in fact, I understand that the distinguished lecturer program is somehow related to the education program. It's an extension. So please, if you are not yet members of the society, please you get in touch with the membership chair, Joy Takamura, or I'm sure you can get in touch with all the people there in Minneapolis. So let me summarize a short introduction. I will be talking about two families of cylindrical micro and nanowires. First part will be devoted to the microwires with diameter in the range of roughly from 1 to 100 microns. And the second part will be dealing with nanowires, also with cylindrical geometry. And the leitmotif for this talk is to discuss the role played by the geometry and the magnetic anisotropy to determine which is the domain structure and the magnetization processes in both families of micro and nanowires for the advancements of different applications, particularly sensing applications. Well, this is a photo of the laboratory in Madrid where we fabricate the different families of microwires. So I will be talking today about two families of amorphous microwires, those produced by so-called in water quenching technique with a diameter roughly between 1 and 200 microns, and particularly on so-called glass-coated amorphous microwires with which they consist of an internal core, which is metallic, ferromagnetic, and amorphous structurally, in diameter 1 to 30 microns, roughly, and they are coated by Pyrex insulating coat. This insulating coat provides insulation from corrosion and electrical point of view, but also introduce significant mechanical stresses. Here I have a couple of videos. I will show you only one of them, but in general, for both families of amorphous wires, it is very important the composition. Those having large content in iron, they show the so-called magnetic bistability, and those with high content in cobalt, but also a small amount of iron. They have nearly vanishing magnetostriction, and they show magnetoimpedance effect. So let me go to the, I wanted to show you this video. So here you see, well, I explained a little bit. We have a Pyrex tube here, you see, and this is a metallic polycrystalline pellet out of the composition we want to prepare the microwire. This is an induction coil to heat the polycrystalline metallic pellet up to 1,200 degrees centigrade. And there is a water jet to increase the quenching rate from 1200 degrees centigrade to room temperature in around 1 millisecond. So the velocity of quenching is about 1 million degrees per second. So you see that with a mechanical machine, we get down the Pyrex with the polycrystalline pellet. So it gets heated up to 1200 degrees centigrade, roughly. And then we need a very skilled person so that manually picks up the molten but very viscous metallic material coated by Pyrex. And then he collects everything in a rotating cylinder here. So it is possible to obtain the microwire with a production velocity of around 400 meters per second, and diameter, as I mentioned, 1 to 30 microns, and coated by Pyrex that can be tailored 2 to 10 microns thick, approximately. So, but this, you see here a picture of the metallic core coated by the Pyrex. So in the process of fabrication, we are able to obtain the microwire, which is going to be characterized and used in sensors later. So the main properties of these two families of microwires, those with large magnetostriction, have bistable magnetic behaviors characterized by a square hysteresis loop. It is practically impossible to get an experimental point in this giant Barkhausen jump, and this is interpreted with this schematic loop in the upper part to the right. So we are in a positive remanence where we have a single large magnetic domain, but at the very end where we have some magnetic charges. Then we applied a field in the opposite direction until getting a critical value when a domain wall depends from one end and moves very fast to the other end. So in the opposite stable state, we have a large domain with opposite magnetization. In the case of cobalt iron based microwires, they are not magnetostrictive, and they are characterized by the giant magnetoimpedance effect, which is a classical effect based in the skin effect, by which the impedance of the material of the amorphous wire drops very drastically when the microwire is put in the presence of a static magnetic field, or it is or when we apply the mechanical stress on the wire. So here I would like to show you a very recent unpublished data on the measurement of the direct measurement of magnetostriction as a function of the applied stress. So in the upper figure, well, we are plotting you see the fractional change in the length. The maximum value, we get a positive magnetostriction, which is 4 times 10 to the minus 8, which is really very, very small. And I think is the smallest quantitatively measured value of the magnetostriction. But if we change just 1% in the composition of iron or cobalt, you see the magnetostriction changes sign and goes to negative. Also very small, maybe not so small, but also really very small. So it is important for me to emphasize that we can tailor the value of the magnetostriction going through the zero value, making small changes in the magnetostriction. Well, actually, the characterization of these microwires is apparently is not very difficult. So for the magnetostrictive wires, we have a solenoid generating an axial field. Inside them, inside it, we have a number of pickup coils, and inside the pickup coils, we have a tiny capillary where we place the microwire. So in this schematic view, you see this is simple. And then to calculate the velocity of the propagating.
1 second, I'm gonna
Velocity.
hunt down where the noise source is from. Let's
Okay,
get some muting.
I see that.
Well, I overmuted him. 1 second. All right, we lost him on that. Let's see if we can get him back. Manuel, we're going to have to reshare here. 1 second. Can you grab control again, Manuel? Yeah, I can't hear you.
You may have to tell him to unmute himself.
Yeah, can you unmute
I
yourself,
don't think you can unmute
Manuel?
him.
Yeah, thank you, John. Let's see. What's the other alternate? I assume you can hear me, Manuel. Okay, so then if you go to the top right-hand side, there's share and mic. If you just go to the mic and unmute yourself and then reshare. Can you do that? The other alternate is if you drop out, maybe you can come back in again. Let's see if I can change your role. Okay.
Can you hear me now?
I can hear you now. Oh, sorry about that.
Okay. And then I go.
And you reshare.
Yes. Do you want me to start from the beginning or?
No, I think this is good on the slide that you're on at the moment. And yeah, you can restart on this slide. And my apologies.
Okay. Yeah, don't worry. So, okay, so just to tell you that to characterize these magnetic microwires, in principle, is not very difficult, apparently. So we applied an axial field with a solenoid. Then we have a number of pickup coils inside the solenoid, and inside the pickup coils, we have our microwire. So the velocity of propagation of the domain wall can be determined just from the considering the distance between two pickup coils and the distance it is like 1 centimeter, something like that, and the distance in time between the induced picked up signal, which is around 1 millisecond, so we can determine the velocity. Here is a plot of the velocity as a function of the applied field. After an initial transient behavior, we observe a linear behavior between the velocity, which is, well, in this particular case, its maximum is 500 meters per second, but can go up to a couple of kilometers per second. So years ago, we studied the dynamics of the domain wall using this general expression, this motion equation, and we determined the different damping mechanisms for the motion of this domain wall. I would like to show you just a couple of examples, in principle, again, very simple experiments, but I think it was interesting. So this, you see, is a schematic view. We have a solenoid. We have two pickup coils, green ones, that are symmetrically placed at the ends of the solenoid. And we have also an additional local field coil that generates a local magnetic field that opposes the field generated by the solenoid. And then this is very important. The microwire is inside the solenoid, but one end is inside the solenoid and the other one is outside. So the magnetic field seen or sensed in this end to the right is smaller. So with that, we are ensuring that the domain wall will be nucleated near the end to the left, and the wall will be moving to the right. And this is a schematic view at the bottom of the domain wall in the middle. This is a head-to-head domain wall in two domains with opposite magnetization. So just for in this plot, you see this is experimental value of the velocity of the domain wall. It's a maximum of around 730 meters per second when we have no local coil. But as we apply the local field coil, we can control the velocity of this domain wall. We can decrease its value, and eventually we can stop the position of the wall in a given position. And this position depends on the amplitude of the local field, also considering the particular value of the driving field. This case was 170 amperes per meter. So what I would like to emphasize that this situation is very metastable to stop the wall in a given position, because the wall is energetically is metastable, so the wall wants to go to one end or to the other. But we can control this position, and this can be important for some applications. And the second experiment, also very simple apparently. In this case, this is another wire. We have the velocity of the domain wall as a function of the driving field. In this case, we do not have any local field coil, but you see there is a linear behavior after reaching this, after the transient behavior, we have a linear behavior of the velocity with the applied field, but we observe two slopes. When we apply the field to the left or to the right, so a negative or positive field, we see that this linear behavior has a different slope. And we wanted to know which is the origin for this asymmetry in the velocity with regards to the direction of the applied field. Okay, so we developed what has been recently a simple model to study the dynamics of the domain wall. Here you see this is the domain wall. We have chosen a parabolic shape, and the magnetization in the domains is not perfectly axial, but because of the experiments, we know that it has some helical component. So it is important to say that the length of the domain wall is much larger than the diameter. It is not to the scale, this scale. And the diameter of the wire is also much larger than the thickness of the domain wall, which schematic view is here. So to study the dynamics, we are using the classical Landau-Gilbert equation for the motion of the domain wall that can be head-to-head or tail-to-tail. And this general expression of the Landau-Gilbert equation has to consider the three components of the magnetization, the circular, radial, and axial components inside the domain wall. Well, here is some equations. I skip the interpretation, but just the final outcome. So we find that depending on whether the wall is head-to-head or tail-to-tail, the domain wall is different. This is the domain wall velocity is proportional to the thickness of the domain wall, and lambda is a parameter, and particularly it's important, it is proportional to the square, the addition of the square of the radial and circular components of magnetization. So we find that these different in the head-to-head and tail-to-tail velocities can explain the difference when we apply the field in one direction or in the other. Well, I have to say also that to feed with quantitative values is not so easy, but well, at least qualitatively, we can understand this behavior. Also, well, let us go now to some applications making use of these families of microwires. First, I would like to show you, this is some years ago, using a microwire for a magnetoelastic signature authentication. So we have a pen, where in the axis, we have our microwire. Well, it's connected to a spring, and at the upper part and the bottom, we have some cables to measure to characterize the magnetic behavior of the microwire. So when we are writing, when we are signing, we are exerting some mechanical stress to the microwire. So finally, the signal we obtain with the cables is we get a voltage with that as a function of time, we get something like that. This is a typical magnetoelastic signature when we are signing. So it is characterized by a number of peaks, positive, negative, and a particular trend. So what we found is that even this, for each person, this magnetoelastic signature is not always the same. It depends on whether you are very happy, good humor, or not so good, and you have some differences. But what is clear, what characterizes your signature is the number of peaks and the trend. It is not so important the strength, the intensity of the peaks and the total time of the signature, but the trend of all these peaks. Another application, so within a European project, we were able to fabricate a magnetic wire, starting with a glass-coated microwire. We spotted a tiny gold nanolayer, and then by electrodeposition, we electroplated an external shell. So this is a cross-section of the microwire. You see the amorphous core, the pyrex in the middle, and the external shell. So we can tailor the behavior of the two magnetic phases. And this is, for example, the typical signal for a soft, hard, bimagnetic microwire. So you see there is two large Barkhausen jumps that are caused by the reversal of magnetization inside in the soft phase and in the external hard phase. So we have used this type of microwires for several applications. I would like to mention some making use of the small angle magnetization rod station technique is a classical technique. We can determine the change of the inductance of the microwire as a function of the temperature. This was well in connection to some application related to close to the temperature of the human body. You see that there is a large change of the inductance in the interesting range of temperature. Also, more recently, we have been able to prepare another patent with making use of these bimagnetic phase microwires that are used as the microactuators. So because these microwires have an intrinsic curvature, which is produced during the fabrication. You may remember that we use this cylinder picking up the microwire. So when we take a piece of this microwire, which has some curvature, and when we apply the magnetic field in one direction, the wire tries to go to get the direction of the applied field. So it can be interesting for some particular application, as I mentioned, as a microactuator. Other very recent application has been developed in Dresden. So here they are using 4 glass-coated microwires in a quadrature, and then there's small coils in each of them to magnetize to saturation these microwires. So the final objective is to create a very, with precision, an inhomogeneous field just in the center of the 4 glass-coated microwires. So in that way, it is possible to generate biaxial field or quadrupole fields, depending on how we prepare the connection of the coils. But also there are many other applications. We have been collaborating with different companies and technical universities. For example, making use of non-magnetostrictive microwires as sensing elements for orthogonal flux-gates. Also, we have used in collaboration with visiting scientists from different countries, this one from Mexico. So we were able to prepare by this rapid solidification technique, rare earth-free manganese bismuth microwires. And here the coercivity is not so large, but the important is it increases with the temperature. Or also we were able also to prepare super elastic microwires out of nickel, manganese, gallium with safe memory properties also. And more recently, I was spending a Fulbright stay last year, last autumn in Boston with Laura Lewis. I'm sure you know her. They were interested in determining which is the influence of a local magnetic field in the regeneration of neurons. So I brought my microwires and in collaboration with a team of bioengineers there in Northeastern University, they have been able to check that the presence of the local field created by the magnetic microwires is sufficient to enhance the growth rate of the neurons. So the origin, the actual origin, is not yet well known. We presented the results in the last GEMS conference in Madrid, and we are still working on to determine which is the origin for this extended growth rate. Well, let me go now to the nanowires. As you may know, there is an increasing interest in the effects of curvature on magnetic nanostructures. Up to now, practically all the nanotechnology materials are based in two dimensions, thin films, multilayers, etc. But what happens when we have a third dimension? That can be achieved, for example, with a flexible film like this one here, nanomembrane, or in the case of nanotubes, nanohelix, or in the case of nanowires, which is our field of expertise. Okay, the case of the nanowires, and because of the cylindrical geometry, in principle, we have, and considering only the shape anisotropy, as for example in the case of permalloy, we have three ground magnetic states: the axial one, the transverse one, and the vortex one. The vortex is characterized by this azimuthal magnetization, but at the very axis where it has to be axial. So, and just depending on the geometry, the aspect ratio, length to diameter, we can have different ground magnetic states. And also in the nanowires, well, here is repeated the figure of the vortex. We have a magnetic singularity in the axis because of the exchange energy restrictions. So in principle, also the skyrmions, well, you know, a skyrmion is very well known. Many people are working on skyrmions in thin films. And well, the characteristic in a cylindrical nanowire is that we can have a so-called skyrmion tube. So a skyrmion tube is like a skyrmion having a third dimension. So it can be characterized along the length of the nanowire. Also, particularly for the case of cylindrical wires, the reversal of magnetization can be produced by transverse domain walls. For example, that is similar to the thin films, two-dimensional thin films, but we can also have a block point domain wall. This is a very metastable situation, and it is so the block point wants to be, like I mentioned before in the case of the microwires, the block point wants to be in one of the ends of the nanowire in this case. So it moves very fast and produces the reversal of magnetization in many nanowires. So we have been working for years in these families of cylindrical nanowires produced, fabricated by electrochemical routes. So first we prepare the alumina membrane by anodization, a controlled anodization process. And then once we have these holes in the membrane, we fill the holes by electrodeposition with the metallic magnetic nanowires. So this is actually the origin why we started to work with this electrochemical technique is because it's less expensive in comparison with other techniques to prepare nanowires. And this is reliable to produce cylindrical wires with reproducible properties. And I can tell you the range of the diameters. We can tailor the diameter from 20 to 400 nanometers and the length from 100 to 50 microns. So we can reach actually a very large aspect ratio length to diameter. Well, this is a schematic view of how we prepare. So we start with a commercial aluminum foil and 1 inch diameter. Has to be very, very pure, at least 5 nines in purity. And after 2 processes of anodization, we get a membrane, which is open by both the upper and the bottom. Then we spatter a tiny gold nano layer, and then we electroplate. This gold nano layer serves as an electrode for the electrodeposition. This is a picture of an array of hexagonal array of nanowires, copper nanowires. But then in the last year, we have been focusing in the study of individual nanowires, and I wanted to show you our results. So we have the nanowires after release from the membrane. The alumina membrane can be removed by the chemical process, and the same with the we can eliminate the aluminium. So we get the isolated nanowires, and then after a tedious process, we have to separate the nanowires by centrifugation and several times. So it takes a time actually, until finally we get an individual isolated nanowire. Okay, so we can prepare in Madrid different families of nanowires. We can prepare nanowires with homogeneous nanowires in same composition and diameter along the whole length, but we can prepare also modulated nanowires. These modulations can be in the longitudinal direction. For example, you see here an image with cobalt gold multisegmented nanowires. They can be, the modulation can be also in the radial direction, so we can get nanotubes or core cell nanowires. And but the modulation can be also in diameter. You see here an image of an individual nanowire with alternating segments with large and small diameter. Finally, though I will not be talking about, but we can also prepare nanowires in a cylindrical template, so having a radial distribution. Okay, that may be interesting for some applications. Well, apart from these nanowires, we have been collaborating with other people to prepare some other nanostructural materials, playing with the electrochemical route, for example, embedding nickel nanowires in polystyrene nanotubes, profiting of the magnetic and mechanical properties of the polymers. We have prepared also large scale nanopatterning by soft lithographic imprint and electrodeposition, or also in collaboration with other people, professors of the Autonomous University in Madrid, who we have prepared highly ordered plasmonic gallium nanoparticles in the upper part of the pores in the alumina membranes. In our group, we have also tried to make use of the magnetic properties of the nanowires, arrays of nanowires for some applications. For example, in another European project, we developed an iron cobalt nanowires and their arrays without rare earth. The objective was to produce rare earth-free nanowires. In fact, the iron cobalt is because in a composition 35 to 65, where we have the largest saturation magnetization of 2.2, 2.3 Tesla. Although we have the problem is that the nanowires are relatively close to have a larger density of magnetic moments, but they are interacting magnetostatically. That reduces a bit the remanence and coercivity. But we were able, in collaboration with people, Professor Farley in Duisburg, to put some ferrimagnets in the ends of the nanowires to delay the reversal of the nucleation of the domain wall. Also, in collaboration with other people in Saudi Arabia and KAUST, with Jürgen Kosel, we're able to prepare core cell nanowires, iron magnetite core cell for some applications. Or in collaboration with the Institute of Nanotechnology in the north of Portugal, in Braga, we were able to prepare nickel segments, starting with the multi-segmented nickel gold nanowires. We got nickel segments that are kind of nanoparticles with a determined preferred direction. So it's like, well, somehow different to the nanoparticles because they have not spherical geometry. And they have proved that these segments of nickel are very interesting as contrast, magnetic resonance imaging contrast agents. Also, I would like to mention other applications. There are several groups. One of them is I think, Beth Stadler there. This is the last application I know from here and from her group on high frequency identification. Also, some of the peoples in groups of Professor Pirot in Louvain, so making use of interconnected nanowires for spin car electronics and thermomagnetic applications, or also the group of Jürgen Kosel in Saudi Arabia for killing by friction tumoral cells, so oncology. So I know also that Beth has been working on that, but well, this is not our work. But importantly, these three-dimensional architectures with magnetic nanowires can be very interesting for storage application and logic memories. So where these, in general, we have to combine lithography and electrochemical techniques to prepare some arrays of nanowires in 3 dimensions, something like reminds on to the racetrack memory or some other type of sensing applications. Well, in our case, once we have prepared the arrays of nanowires, we characterize the array first. This is the hysteresis loop of an array of nickel nanowires, the black points. And here to the right, we have a magnetic force microscopy image of an array where you see black and white points indicated that individually it's a black or white point. It corresponds to one individual nanowire. So indicated that some of them are pointing up, the magnetization, in some others the magnetization is pointing down. So I have another video. Oh, sorry. Let me try to show you the. I hope you can see when we apply a magnetic field parallel to the wires, some of the white points becomes black, indicating that the wires reverse magnetization individually. Until getting, well, the applied field in that case was not large enough to reach saturation. But, well, okay, go back to the laser. So you see the black, the red points correspond to the hysteresis loop obtained through the magnetic force microscopy imaging. So in fact, each point, the magnetization can be determined just by counting how many black and white points we have. Okay, from now on, I'm going to talk just on individual nanowires. First thing is that it is very important in the case of these nanowires, the role played by the crystalline structure. Here, you see in the upper part, there is a single crystal with cubic symmetry, atomic symmetry. It's an iron cobalt nanorod. This case was a longer nanowire, a few microns in length, And at the bottom, we have a single crystal of cobalt, which structure is hexagonal HCP. So I would like to emphasize that the magnetocrystalline anisotropy in a cubic crystal is much smaller than in the case of an hexagonal or uniaxial anisotropy. So in the case of a cubic crystals, so the shape anisotropy is typically larger than the magnetocrystalline anisotropy, but not in the case of the hexagonal crystals, where we have to consider the fight between the hexagonal magnetocrystalline anisotropy and the shape anisotropy. Then let me show you which is the result for individual nanowires in the series cobalt nickel with different content in nickel. So if we have a wire with large content in nickel, cobalt 35, nickel 65, we know that it has a cubic structure. So the magnetic force microscopy image in the remnants, we have a magnetic dipole, an ideal magnetic dipole with two charges, black and white at the very end, causing some stray fields near the ends of the nanowires. Here is the experimental. The noisy hysteresis loop is the experimental hysteresis loop obtained by magnetoptic Kerr effect, and the blue one is the obtained by micromagnetic simulation. But what happens when we change the composition and we go to, for example, cobalt 65, nickel 35? Here, we know that in this wire we have some regions with HCP crystal symmetry, another with cubic symmetry. To determine the domain structure in this wire, we have used the synchrotron. We have used this technique of photoemission electron microscopy with X-ray circular magnetic dichroism, and you see here a schematic view of the cylindrical nanowire. Some of the incident rays are reflected. These reflected or photoemitted electrons give us information of the magnetic structure, magnetic distribution of magnetic moments in the surface of the nanowire. But some of the X-rays are transmitted. These transmitted X-rays give us information of the internal part of the nanowire. So we get information of how the magnetic moments are distributed inside the nanowire. So if we go back to the image obtained by PIM with the circular dichroism analysis, we see some region with multi-domain structure here with the transverse domains. But here to the right, we have completely different contrast. We have here two vortex domains with different chirality, according to the interpretation of these images. So it is very important that we can have different domain structure depending on the crystal symmetry. And for example, we were able, in collaboration with people in France, through the electronography analysis, we were able to obtain also some kind of, we call the exotic domains in cobalt nickel alloys, where you see in one locally, in this red region, we have a hexagonal crystalline structure with vortex and transverse domains perpendicular to the axis of the wire. While as we move to the right, we have this blue region where the crystal is cubic, and we have finally axial magnetization. And this has been obtained also experimentally in collaboration with a group in Dresden through holographic vector field electron tomography. We have also the same structure as these exotic domains I mentioned before. So we can have a very complex domain structure in these nanowires, depending, of course, on the crystalline structure and composition. Let me go now to the modulation in diameter. As you see here, two images of these individual nanowires with segments with different alternative segments with different thickness. And this is all the antinodes structure of modulations in the diameter. I will be talking only on the first one. So this is an electronography image of a, modulating nanowire. So you see, this is the nanowire, the small segment with a small diameter, and you see these colorful lines with arrows. What we are saying here is the stray fields, the induction field, the magnetic field outside the nanowire. So we can see here that in the transition region between two different diameters, we have some accumulation of magnetic charges. So there's a positive and negative magnetic charges. So this is in the bottom, we have a larger image of a number of different modulations in the diameter. We have also done some micromagnetic simulations of these nanowires with different diameter. I will not pay too much attention. I think I am already 45, 47 minutes. So, but we can, through these micromagnetic simulations, we have been able to distinguish a weak pinning to what we call corkscrew pinning. So when depending on which is the difference in diameter between the large segments and the tiny segments. When the difference in diameter is large enough, we have what we have called corkscrew pinning that is characterized by a vortex or kind of schemion tube inside the large segment where the axis is not perfectly the axis of the nanowire. So it's having a kind of cork screw like in the figure here, schematically to the left. Well, this is concerning the micromagnetic simulations. And okay, finally, the compositional modulation in the nanowires. The objective is to have first a segmentation with different segments having cubic or hexagonal magnetic anisotropy, depending on whether this the crystalline structure is different. The second modulation can be ferromagnetic and metal. Well, the first simulation, the first modulation in composition, here we have a topological image where we have cobalt, nickel, and nickel segments, where they are very well differentiated from cobalt. The transition from one to the other is very sharp. And at the bottom, we have a magnetic force, PIM images, where we have the cobalt nickel, which is hexagonal. We have two vortex with opposite chiralities here. The nickel segment magnetization is axial, and so on. The cobalt nickel, we have vortices, and in the nickel, we have only axial domains. Well, we have been also doing some simulations. I would like to mention the very last experiment we have done also on this type of cobalt nickel multi-segmented nanowires with the transmission X-ray microscopy, also with circular dichroism analysis. So which is interesting here, has been recently published. So we can determine which is the distribution of the magnetic moments along the length of the wire. So in both cobalt, nickel, and nickel segments, but also in the radial direction. That you see here the experimental results obtained from these measurements, where we see the distribution of magnetic moments depending on the distance to the radius, to the axis of the nanowire. We have here a single vortex in the left part of the large domain. We have an axial domain in the nickel, and we have a three-vortex structure in the segment to the right. Well, and finally, the multi-segmented nanowires with design length in the magnetic segment. So here we have iron, cobalt, copper. So with copper, you see the copper is the white contrast here. You see the length of the magnetic segments, iron cobalt segment, is small in the left part of the wire and increases, being much larger, increases continually up to the other end. So this modulation with increasing length of the segments magnetic segments was introduced artificially during the process of fabrication of these modulated nanowires. Well, this is a magnetic force microscopy near the end of the nanowire at the remanence. And also, I would like to mention that we have done this type of experiments in these multi-segmented nanowires, and we have found what we have called the magnetization ratchet. So you see, to the left, we start with a single domain structure is white contrast under a negative field of minus 700 Ørsted. As we remove the field and we apply the positive field of increasing amplitude, we see that the magnetization reverses in different steps after reaching a negative contrast. So, but interestingly here is that the reversal starts at the end where we have the shorter segments of magnetization, this shorter segments of iron cobalt. So, and then if we start with the opposite situation, we start with a black saturation under a positive field, and we started to apply a negative field of increasing amplitude. We observe again a reversal of magnetization in different steps as we increase the field until getting the final saturation. But interestingly, the reversal occurs also starting from the left end of the nanowire, where we have the shortest segments of magnetic segments. And it is possible to reconstruct the hysteresis loop of this individual nanowire. Well, the micromagnetic analysis of this magnetization reversal process has been performed. Well, this is a video schematic. You see the schematic signal of the different segments. So the reversal starts near one end and propagates toward the right. This is what we call magnetization ratchet because magnetization reverses from the same end unidirectionally, independently on which is the direction of the applied field. So actually the origin for this unidirectional reversal can be determined. We think it according to these simulations is determined by the demagnetization process of the segments. So the segments to the left, which are smaller in length, have a larger demagnetizing effect. So it is expected that these segments reverse magnetization at a smaller field, and then this reversal propagates along the entire length of the nanowires. Well, I think so. I would like to give a few minutes for questions. So there is a couple of slides. If you are interested, you can ask me later. So we have made some experiments with the current poles through the wires, and we have determined the modification of the domains on their different current pulses. Also with some micromagnetic simulations on the action of the reversal on the electrical current and magnetic field. And with this, I think that we can finish well, there is a number of perspectives concerning both micro and nanowires from basic but also applied technological applications. But this is the last slide. I would like to mention is a picture of the group just before the COVID, actually, 4 years ago. This I would like to mention the role played by Christina Brand, who has been responsible for the fabrication of these modulated nanowires. Agustín Asenjo has been responsible for the magnetic force microscopy imaging. Rafael Pérez del Real has been responsible for the magnetooptic Kerr effect and some applications, and Oksana Chubikalov-Esenko has been responsible for everything related to micromagnetic simulations. And with this, I thank you very much for your attention. I think we have some minutes for some questions.
Yeah, thank you very much, Manuel. So let's open the floor here for questions.
I had one.
Go ahead, Ben.
Yeah.
Okay. Thank you for a really interesting talk. It's a great summary of so much good work over decades, and nice to see it all together and explained. So I appreciate that. So
Yeah.
your slide that had the quadrupole from that you worked with Dresden had a scale bar, and I'm assuming that well, those microwires there were like hundreds of microns thick. So maybe that scale bar was millimeter or less. What I'm really wondering is how small can you control the quadrupole field from your microwires? Yeah, that one.
Yeah, okay. So these microwires are glass-coated microwires with a diameter, I don't remember exactly, between 5 and 10 microns in diameter. And the length was, I think it's in the order, they use maybe 1 centimeter of at least some millimeters in length. So it is possible, you see here to the right, the magnetic field, the amplitude of magnetic field and up to 100 megahertz. So it is very local, the field, and we have a really, well, what was the question?
Well, the spacing between your probes there is probably on the order of microns, hundreds of microns.
The what? Sorry,
the spacing between the tips.
Yeah. This is we can check in the paper. This is something like hundreds of microns. So or maybe less than 100, because the diameter is, I don't remember exactly. It is between 5 and 10 microns in diameter, and to see. So the distance between the microwires, the tips of the microwires, should be in the order of 20 microns, something like that, 20 to 30 microns.
Yeah. I'll look up that paper again. Yeah. But I had one more question, if I could. I see there's maybe another, but also where you were watching the switching of the nanowire array from the top, it almost looked, and maybe because it went too fast, that one of the wires might have switched back to white, maybe from dipole fields, or maybe my eyes just didn't watch the whole picture very well, this one. So if you play that movie, it looks like the ones in the upper left, upper right corner, some of them turned black and then turned white again, which is very interesting, because I think that would happen, right, with dipole fields. Yeah,
I understand. And I agree with your comment. So, in fact, as some of these nanowires reverse magnetization, the local magnetic field in the surrounding changes, and it can be that eventually one individual wire changes the color and get backs again. So because in fact in this if we go to the left, there is another magnetic force image at the remanence, but considering a wider region in the array of nanowires. So you see, this is kind of labyrinthic structure, evidences the large magnetostatic interactions between the nanowires. So you are right. So the reversal of, so in order to get a hysteresis loop, we have to count all the wires. Well, not particularly you or me, but the machine can count how many wires we have, black or white. But you are right. Locally, the magnetostatic field produced by the surrounding wires can change, and in fact reverse again the magnetization. Is that what you?
Yeah, that's what I thought I saw, but the movie went quick, and it's pretty interesting. I don't think I've given a lot of thought to that when we're looking at reversal. So it's fun to see it. Yeah.
No, but I think you're right. So if you want, I can go ahead to the video, but for that, I need to change.
No, we can take other questions, maybe if there's time after those.
Yeah, I think we just got time for one last quick question. Well, then you can go directly to it if there isn't that quick question. Do you want to try?
The video? Great.
Go ahead.
Is it possible then to play it again, Manuel?
Yeah. Okay. Yeah. Sorry. Yes.
I'm watching the line that's forming diagonally up to the right.
Yeah.
And I saw one of the wires switch back. There it goes, back to white. It had been black and then it goes back to white, which is in the opposite direction of the field, right? You know, the other thing I was thinking about with this hysteresis loop you have here, it reminds me of a paper when I was first working with media with Randy, that the slope would be 4 pi, 1 over 4 pi, if there was a lot of dipole interactions between, in that case, it was grains of magnetic media. And I'm wondering if that slope would match that 1 over 4 pi.
Yeah, actually, this is as well. There's some publications related to the effective, how to say, magnetostatic field in the surrounding of an array. Well, you have to consider the diameter of the nanowires, the distance between. Well, this is these are hexagonal arrays, but having also some domains with this hexagonal arrangement. So we can go from one domain to other, and this is some differences. But yes, it is possible to. I don't remember. It's not 4 pi exactly, but some with other parameters we have to take into consideration the aspect ratio of each nanowire, the length to diameter. So the kind of the magnetizing field plus the interacting with other nanowires. But this is related, so you're right. It is related to 4 pi, but not exactly 4 pi.
Right. With that, unfortunately, we are now over time. Let's thank Manuel very much for his presentation.
So
And,
thank you very much. It has been my pleasure to talk to you.
Yeah.
I hope we can meet in person very
hopefully
soon.
hopefully we'll get a chance to meet you physically, face to face again very soon. Thank you, Manuel, again.
Okay. Thank you.
Thanks, Manuel.
Thanks.
Bye-bye.
Bye.